Hi, my name is Eric Kolvek, and I'm a member of Team 7, also known as a matter of Fadden, we aren't going to make money. Today I'm joined by my teammates, Reachel Zhang, Samantha Brisgone, and Abdullah alaboudi. We are here today to talk to you about our design project for a dimethyl ether synthesis plant. To start today off, we're going to talk about our project definition and our process design. Going forward, we're going to get into the economic analysis and determine whether or not this process is actually feasible. And after that, we're going to go straight into our professional recommendations. So Team 7 was tasked with the designing of a dimethyl ether synthesis plant and determining its economic viability. As shown, this is the main reaction that we based our entire plant after. It is a methanol dehydration reaction, and we chose a high temperature gamma alumina catalyst to drive the reaction forward. Additionally, as you can see, water is created as a byproduct. So the plant will be built on Nitlion's current Gulf Coast complex. This has a lot of pros associated with it. Firstly, since it's being built on an existing complex, that will save a lot of money in having not to break any ground. Additionally, it's located near a methanol feed, and now although this isn't the most ideal methanol feed, with 5% mass impurity of ethanol, 3% of acetone, 2% of water, and 0.5 ppm chloride, it is relatively close and has the ability to save us a lot of money. Additionally, with the Gulf Coast climate being as fair as it is very ideal for any chemical synthesis. You spend a lot less money on having to heat reactants going into different parts of the process. And finally, who want to live in this beautiful scenery? And now I'm going to pass it off to my colleague Samantha Brisgone to talk about product specifications.
Team 7 was tasked with creating a DME synthesis plant that would meet target production and purity specifications. And these specifically are for dimethyl ether at 98.5 weight percent pure, and also for methanol less than 0.05%, and for water less than 0.03%. And the remaining percentages would just be other impurities that would come from the reaction. And our target production rate was 70,900 pounds per hour. So after modeling the reaction in Aspen Plus, we have found that our out of the DME distillation column, we've exceeded the 98.5% purity specification and achieved a 99.2% with a 0.08% impurities. And our impurities, after adding the lubricant to the DME production stream, as you can see, we have 56% of the impurities include the lubricant, 33%, the next greatest are methoxyethane, and the others are methanol at 5% and acetone at 6%. And in total, we have achieved exactly 70,900 pounds per hour. Now, when designing this plant, we considered a sustainable engineering approach to be able to make sure that our plant lasts a long time and benefits everyone around it. And to look into a sustainable plant, we need to consider the environmental impacts, specifically the carbon impact that our plant has on the environment. Also considering the societal benefits from our neighboring community and as well as the global impact. And lastly, considering the economic benefits that our plant can provide. Lately, there's been a lot of talk about DME in the fuel and automotive industries, that it is a new clean alternative fuel. At a DME industry workshop in Ford, Germany, one of the companies stated that DME is an ideal replacement for diesel fuel, and it lets the drivers keep their high efficiency engines, but also eliminating any emissions. And it's also driving some legislation in certain cities in the US and also countries around the world to eliminate the use of diesel motors because of their bad effect on the environment. In order to reduce any emissions that will come from our utilities in our plant, we chose natural gas boilers, which produce a 93,312 pounds per hour of CO2 equivalents. Now, to give some context, natural gas boilers that are well maintained are 99.9% efficient, meaning that if the combustion is complete, then only CO2 will be emitted. In the small chance of a 0.1% incomplete combustion, then other harmful pollutants will be created, but it's a very small chance. In addition, after doing an analysis of different sizes of natural gas boilers that we could use, we found that the small controlled natural gas burners with the low NOx burners and flue gas recirculation give off the least amount of emissions. So this is something that we aim to use in our plant. And also from an EPA fact of 2017, the CO2 emissions, comparing that to the emissions of our plant, was 0.0057%. So our plant made up for a very, very small amount of emissions in just 2017. So that means that we won't give off much in the coming future if this plant is to be built. Some societal benefits of the creation of our plant include economic growth of the community, as well as challenging the global fuel industry. Our plant promises a lot of economic growth through providing jobs to local businesses such as contractors and the methanol production plants, as well as just local union workers and people to be able to manage and run our plant. In addition, it challenges the global fuel industry because introducing a DME synthesis plant may urge other countries and cities to pass more legislation eliminating the use of diesel fuel engines, which will create a cleaner environment. When analyzing our plant for any economic benefits, we found that the supply chain of methanol is a very beneficial feedstock because there's endless ways to create the methanol, and it's very abundant around the world. The ways to create it are through natural gas, coal, renewables such as municipal waste, and as well as petroleum fractions. Now, natural gas is the most common way of creating methanol and what we will find most from our vendors, so this is most likely the way that it will be created for the methanol that we are purchasing. The methanol is then purified at a methanol production plant and then sent through rail car to our plant. And because there's so much methanol plants around and near our plant in the Gulf Coast, there'll be lesser costs for it to be shipped to our plant, which will also save us money in the long run. And now I will pass this off to Reachel Zhang, which will talk more about our process diagrams.
So our team considered various design options, but we ultimately decided on one base case block flow diagram as shown here. So we start out with the incoming methanol feed, which, as mentioned earlier, contains traces of ethanol, acetone, water, and chloride. So the first step of the process is to remove the chloride through an ion exchange column, and the purpose of this is to prevent any corrosion that may occur as a result of the corrosive properties of chloride ions. And we also wanted to avoid having to use more expensive corrosion-resistant material throughout the system. The remaining stream is then sent to our first distillation column, which is meant to further purify the methanol stream. And it does this through differences in boiling points. The methanol and the acetone are sent overhead through the distillate stream to be fed straight into the reactor. And the reason why we fed the acetone into the reactor is because any side reactions that occur as a result of the acetone were shown to be negligible. And the reactor is where our methanol dehydration reaction occurs to form our DME product, again at a high temperature using our gamma alumina gas phase catalyst. The product stream containing our DME then goes into our DME distillation column, where it is purified to meet specifications, and we achieve our 99.92% pure DME product at 70,900 pounds per hour. It is then combined with a lubricant so that it can be sold as a sellable product and then sent to OBL storage. The bottoms of the DME column, which contain remaining impurities and side products that formed as a result of the side reactions in the reactor, are then sent to another distillation column, which purifies the remaining methanol and recycles it back to the reactor. And this is meant to improve the conversion of methanol to DME in the reactor without having to increase our methanol flow rate. Out of this stream, 24% of the stream is then purged to avoid accumulating impurities throughout the system. The remaining products that come out of the bottom section of the distillation column are then incinerated due to the fact that they do not meet wastewater treatment specifications or the ability to be burned off as fuel. Okay, so going back to our first distillation column for the methanol towards the beginning of the process, the bottom stream contains mostly ethanol, water, and remaining methanol. The remaining methanol stream is then sent to another distillation column so that it can be further purified to be a sellable product. The specification for methanol to be sold is that it is 99.8% pure, and our product is 99.9%. It is sold at a rate of 1,010 pounds per hour, and it is also sent to storage. And then the remainder of the stream at the bottom is then incinerated as well. And now I'll hand it off to Abdullah alaboudi to discuss the economics of the plant.
The capital cost for building our plant is 89 million, which is divided directly or indirectly to OBL and IBL. 25% of our capital cost coming from the OBL and the rest coming from the IBL. The breakdown for the IBL cost coming from the equipment, including the piping and every allocated cost, is seen in this graph. We're showing that the heat exchanger is the most expensive thing, as well as the drums. So most of the 42 million IBL cost coming from these two equipments. Then it will be the distillation towers, and the last and pump and the reactor will be not that high comparing to the drum and the distillation tower, the heat exchanger. For the OBL, it's 14.1 million cost, and it breaks down into four categories. The first one will be the site development, and the cost for that isn't changing even if we decrease or increase our production rate, as well as the environmental. However, both the cold water increase, as known as the utilities, also the raw material and the product storage tank is changing with the capacity of the production of the plant. As well, these values have been changed from the year that was given to the 2020 to have accurate number for how much these will gonna cost. And as you can see, utilities is the most expensive thing to build in terms of OBL. Then will be the raw material, due to the high rate of production we have. For the total cost, ongoing cost the plant will have, which is including the raw material, utility, fixed cost, and the CG&A. The total of these will be 547 million a year. The most expensive thing is the utilities, and mainly because the waste. Most of the waste is in the utilities, causing that will be to go high. Then will be the raw material, due to the fact that our production is very high. For the fixed cost and the CG&A is very much low, less than 10%, and our byproduct is lowering our ongoing cost, but it's less than 1%, which is coming from burning the birch to a fuel and selling the 1,010 pounds of methanol per hour. So the cost of 1 pound of DME in terms of raw material and utilities. Raw material combined contributed to $0.263 per pound of DME in terms of cost. Most of that is coming from the methanol, which is the feed of our reaction, and then the chemicals, which are money paid for each methanol we have in the system, which is 0.9 cents per pound of methanol. And that's why it's the second largest, since our production rate is very high. In terms of DI water, catalyst, resin, and lubricant, they are very low, that we can assume they are less than 1%, even 0.5% to the raw material cost. In terms of utility, the utility combined is $0.65 per pound of DME. Most of that is coming from the waste, which coming from the two streams we have, which is the bottom stream of distillation 201 and 501. Then the rest of the utilities are streams or cold water, chill water, hot oil to cool down or heat up the streams, since most of the streams, even if it will be incinerated, need to be sent to the storage with a normal room temperature. And that's why we have a lot of utility used in the system. The income of our plant coming directly from the production of the DME, which is sold at 21.5 cents per pound, and also by selling the byproduct of methanol, which is 19.1 cent per pound. As shown here, most of our flow rate is DME, and we are producing a very small amount of methanol. For the economic of the plant, unfortunately, the plant have a negative cumulative cash flow over the 15 years of operation, as can be shown in the graphs. And in NBV at 12% is negative 1,795 million, and due to the huge loss of the production or the plant, we aren't able to calculate the amount of investment rate of return. However, the investment rate of return at 12% could be calculated if the price of DME was set to be 95.5 cents per pound. Unfortunately, in the initial calculation was set to be 59.4 cents per pound. Unfortunately, this number is wrong, so the correct number is 95.5 cents per pound to get rate on investment ratio at 12%. And now move over to my teammate Eric.
Additionally, our team has analyzed a bunch of different ideas and aspects that we could potentially change to our process in order to better the economic situation. Firstly, we're considering purchasing a pure feedstock, more specifically a more pure methanol feed. If we can do this, it would benefit us in terms of capital cost and utility, because we wouldn't have to spend as much money on purifying the methanol. Additionally, we're considering using the separated ethanol to produce diethyl ether. Overall, this component is sold at 38 cents per pound, which is actually significantly higher than our DME and methanol. So this could potentially serve as a very viable product source. And finally, we're looking to increase the waste management in order to decrease costs. The vast majority of our utility costs are being used up by having to incinerate our waste. So if we can add more management to have our waste meet specs, that could potentially save us a lot of money. It is Team 7's strong recommendation that all of these aspects are looked into thoroughly to potentially salvage this project. Unfortunately, it is not feasible to implement this project as of now, because as a matter of Fadden,
We aren't going to make money!
We would like to acknowledge our Professor McFadden and Dr. Aurand.
Our mentors, Jessica Geist and Alex Okert.
Our TA Nick.
and I'd like to thank my wonderful team.